This lesson contains a description of just about the simplest applet that can be loaded and displayed in a web browser. Now, a web browser doesn't know about applets, it knows about HTML, so everything starts with an HTML file that we feed to the web browser. The HTML contains an applet tag that names the class file and specifies the size of the applet window. Here's a very simple HTML file. There it is. That's the entire web page. All it does is display a single heading line and an applet. It was kept simple on purpose so you could see the form of the applet tag. Three things are specified in the applet tag. First, there is the name of the class file, then the height and width of the window. That's right, an applet has no control whatsoever over the size of its window. That's under complete control of the web browser. And the web browser gets it from here in the applet tag. If you omit the height and width tag, it's an error. Different browsers will do different things, but I'll bet none of them will do what you would like for them to do. The source code of the Howdy applet looks like this. You already know most of what there is to know about the internals of an applet. It's a component that displays an empty window like a canvas. It has a paint method that's passed a graphics object just like any other component. The Howdy Applet class extends the Applet class, which is a member of the Java Applet package. It's a component. That is, it extends the component class, so it has things like the paint method. As we'll be seeing, it has lots of other things that we've been using in the previous examples, such as threads and the update method. And it has some extra stuff, too, because of the special requirements of living inside a web browser. In this simple example, the applet does nothing but display a string of characters at a fixed location in the window. By using the appropriate section on the File menu of your web browser and then looking around until you find the JWork directory, you get a list like this of the names of the files in the directory. The only one of these that a browser understands is the HTML file, so let's select that one to be opened. The heading text and the applet window are displayed as we expected. You might want to note that the default background color is different from the default background color of a regular Java application. In fact, different web browsers will have different Java plugins installed, so nothing particularly standard happens when you let things default. In an applet, even more than in an application, you need to try to specify everything. People want to know how long it takes to load an applet over the internet. It seems that applets have a bit of a reputation for being slow to start. Well, it's quite true for large applets. You can take a look at the size of the class file and get some idea of how long it will take to load. Here you can see that the class file is only 368 bytes, so it loads quickly even over a dial-up link. But of course it doesn't do much either. The more code you put in your applet, the larger the class file and the slower it loads, but it depends on the application. A well-written Java applet can do more than anything else in a web browser. For example, I do a bit of stock trading online through an applet that takes almost 10 minutes to load. But once I have it loaded, it keeps me up to the second with all the information I need. So I only have to load it once in the morning and I'm good for the day. But there are some jobs for which an applet is just the wrong tool to use. Oh, there's no such thing as a rogue applet. In a regular web browser, an applet cannot access anything that could cause harm. In particular, a remotely loaded applet cannot read or write to your local disk drive. There was a bug in an old version of Netscape that provided a loophole around this, but that old browser doesn't exist anymore and the problem has gone away. All that's left is the rumor that an applet can be evil. There's a handy little tool that you should be aware of. It's a program called the Applet Viewer. You get it free as part of the Java installation. If you feed it an HTML file, it throws away everything in it but the applet tags and displays just the applets. Here, let me show you. It's a great tool to use while you're developing applets. For one thing, it's very picky about the HTML syntax, and for another, it won't load an old version of the applet in its cache the way a web browser does. It always shows you exactly what you've got in your current class file. Oh, and by the way, the first time you run an applet in the applet viewer, you'll probably get an error message about a missing Applet Viewer Properties file. You can ignore the message because before you're finished reading it, the Applet Viewer creates a default configuration file for you, and you won't ever get that error message again. An applet has a definite structure that you need to be aware of. Like any other class, an applet can have a constructor, but it also has special methods named init, start, and stop. Here's a simple applet contrived to demonstrate the basic structure of an applet and how these methods are used. The variable named count is initialized to 1 and is displayed and incremented in each one of the methods to demonstrate the order in which each method is called. This constructor just prints out an identifying line of text and increments the count. Now, here's what happens in an applet. The web browser finds the applet's name in the HTML and passes that name to its Java plugin. The Java plugin reads the class file and executes a new command on it to create an object of the class. Whenever the new command is executed on a class, the constructor is executed. So it is the constructor of an applet that is the first code to be executed. Well, the first code to be executed is the initialization of the count variable, but that's a little deeper than we want to go right now. The next thing that is done by the Java plugin is to call the method named init. When you write an applet, you can include an init method, and it's guaranteed to be called before any of the other methods of the applet, such as paint. So you can do some initialization in here. The reason for the existence of the init method is so you can find out how big the window is by calling getBounds. You can't call getBounds from the constructor because the size isn't known yet. I'll be showing you how getBounds works in an upcoming session. After init, the start method is called if you need to do something to start your applet running. Once the start method is called, the paint method is then called with a graphics object, and the applet can use it to display itself in the window. When the window displaying the applet has disappeared, the stop method is called to let the applet know it can quit doing whatever it's been doing. The start and stop methods are perfect for managing animation, as we'll see later. Let's compile and run this applet so we can see the order of things being called. I pre-prepared an HTML file. Now this is another good reason for using the applet viewer when developing applets. You can print text and it will come out on the screen like this. It's handy for debugging. Anyway, you can see that the constructor executes first. Next, it's a call to the init method. The init method is called exactly once in the entire life of an applet. Next, the start method is called to kick the applet off and get it running. Then the browser calls the paint method to have the applet display itself in the window. The browser may call the paint method any number of times, and every web browser seems to have a different pattern for calling it, but you need to be ready for it to be called again and again at any time. Now look at this. We minimize and bring the applet back up. When the window of the applet is obscured, the stop method was called to halt whatever action was taking place. Then, when the window appeared again, the start method was called to get it going. Then, because the window needs to be refreshed, the paint method was called to put stuff on display in the window. At the very end, when the applet is shutting down, the stop method is called. That's pretty much the life cycle of an applet. You can count on the paint method being called a lot. The start and stop methods may be called any number of times, but they will always be called in order. That is, the start method is always called first, and from then on they alternate. Neither start nor stop methods will be called twice in a row without the other being called. The stop method is always called last. Oh yes, there's also the update method that's called whenever you call repaint, and the run method for animation, and that just about wraps up the predefined method names. It may seem like a lot to remember, but I'll be giving you some good examples you can use as starter applets when you want to write your own. That's the way I write an applet. Whenever I want to write an applet, I'll look around for one that's sort of like the one I want to write and copy it as my starter. Then I rip out all the stuff I don't need and build a new one from there. That's why some of my programs have extra import statements. I always seem to leave something from the previous program that I don't need in this one. An applet is very much a creature of the Internet. It's meant to be downloaded by a web browser, and its job is to display stuff inside the window provided by an HTML page. And it's not allowed to access the local disk of the computer for any reason, but it is allowed to access the server's disk drive. This applet loads an image file from the server and displays it in the browser window. That's all it does, and you'll recognize the process as we go through it. This line of code declares a reference to a URL object and then calls the method getCodeBase that produces the URL. The codebase is the directory from which the class file was loaded. As an alternative, the URL could have been retrieved by calling the method getDocumentBase, which is the directory in which the HTML page is stored. Now, these are the only two URLs you're allowed to use for reading and writing files in an applet. It's that security thing. By using the URL and the name of a file, you can read and write any file found in that directory on the server, or any file in a subdirectory of that directory, but nowhere else. Anyway, to load the image file, a call is made to the method getImage, specifying the URL and the name of the file. But just like was done earlier, this doesn't load the image. It only schedules the loading of the image, and we have to use our old friend the media tracker to find out when it is actually loaded. And just like we did before, this program calls the waitForAll method to just wait until the entire image is loaded before going on. It's important that you choose something intelligent to do in here. Over the Internet, there are lots of things that can go wrong and cause the loading of an image to fail. It's also wise to check whether there is any data in the loaded image. If it exists but has nothing in it, it will load just fine and display perfectly, but you may be a bit confused about what happens when nothing shows up. More than just a bad file can cause this condition, so it's best to check for it. All that's left of this applet is the paint method that displays the image. Oh, I created an HTML file with a window large enough to contain the image. This creates a window 450 by 450 pixels and turns it over to the applet for display. Running the applet with the applet viewer looks like this. And here's the whole world. Notice that the window is a little bit larger than the image it displays. There are a couple of things you can do to cure this. You can measure the size of the image you want to display and then specify those exact dimensions in your HTML. On the other hand, you can call the getBounds method to determine the size of the window and then produce a scaled image to fit it. But you have to be careful. If you rescale the image to fit the window size and then write the HTML so the window is oblong, the world comes out looking like a football. Let's say you're going to write an applet that's going to be used by other folks in their web browsers. You need to consider the version of Java installed in the web browser. Under different circumstances, applets have different audiences. One very common use of an applet is to provide an interface used inside a company. Some are for providing an interface to clients, others are for general use on the Internet. The point is, in some cases, you'll have very specific information and even some control over the version of Java that will be used to read the applets. In other cases, it can be any web browser and any old version of Java. There are lots of browsers out there, and the number is on the rise. There is Opera, Netscape, Mozilla, Conqueror, and more new ones every day. There are also browsers for several operating systems, such as the different versions of Unix and the Macintosh. This lesson is about the things that you'll need to consider before you release an applet into the wild. When you compile an applet into a class file or a set of class files, each of these class files is imprinted with some special identification numbers. The first 8 bytes of a class file are used to uniquely identify it as being a Java class file. In the world of Unix, a number embedded in a file for purposes of identity is called a magic number, and a Java class file has its magic number. Any number could have been chosen, but somebody had a sense of humor. When the first 8 bytes of any class file are displayed in hexadecimal notation, they spell the words Cafe Babe. Following the magic number are the major and minor version numbers. These are the numbers that can make a difference to you. These are the common revision numbers. For example, in Java version 1.4, the major number is 1, the minor number is 4. And here's what's important to you about that. A Java virtual machine also has a major and minor number, and a Java virtual machine will not attempt to execute a class file that is a later version than itself. For example, if the Java plugin in a web browser is version 1.4 and your applet is version 1.5, it won't run. But there is a simple solution to the version number problem. You simply tell the compiler to produce a version of the applet for an older version of Java, and you get to pick the version. You do that by compiling the applet with the target option like this. In this example, the class named MyApplet is being compiled as a version 1.2 class file. Actually, 1.2 is a pretty good version to choose because you have virtually every web browser that is capable of running Java with version 1.2 or later installed. Also, version 1.2 is the first of the Java 2 series, so it has most of the capabilities of the newest versions of Java. The only thing missing is some of the more advanced classes, and the odds are very good that you're not using any of those anyway. The second area of concern is not nearly so important. If you use different fonts, you need to use something that's likely to be installed in the browser. Of course, if your applet selects a font that's not installed, the plugin will simply use the default font, so your applet will still work. But it would be best if you could choose from fonts that have a high probability of actually being available in the target web browser. Certain font names are used in almost every web browser. If you expect to be doing a lot of applet work, you need to experiment with these names to see what happens. Some of these names will be the same font on some systems. For example, it's common to have serif and Times Roman be the same font, and on some systems, sans serif and Arial will be the same. Also, that last one, the Zap F Dingbats, it's virtually useless as a font. You could use it for decoration, I suppose, or if you wanted to cast an evil spell of some sort. Anyway, if you watch your version numbers and your fonts, everything else will pretty much be taken care of by Java. By the way, some browsers can't load the Java plugin, and some of the older versions of the Microsoft browser won't run Java under any circumstances. Those folks will need to update their browser to get Java. Java first became known for its animation of applets. Today there are all sorts of ways of having things jump around on a web page, but it all started with Java. While animated applets are no longer the centerpiece of Java, it's still quite common to see them. This is the Applet version of the no-flicker program presented earlier. Many things are the same, but there are some differences that are important. Here is the declaration of a Boolean variable named running. It's used to turn the animation on and off. It's initialized to false to indicate that the animation is not now running. The size of the window is fixed by the web browser, so we retrieve the size information here in the init method so it'll be available for the rest of the program. The value of x is set, positioning the ball off stage to your left. Remember, the web browser calls init before it calls anything else. Now the web browser will call the start method to get things going. If the animation is not running, a thread object is created and its start method is called to get it going. Then the flag named running is set to true to indicate that the animation is underway. Now it's probably not absolutely necessary to test the running flag here because it's only toggled in start and stop, and the browser does promise to call them in the right order. But I've dealt with enough strange web browsers that I don't trust anybody. I suggest you put this check in your animated applets too. To turn off the animation, all that needs to happen is the running flag gets set to false. This is the animation loop that contains the call to sleep and the call to repaint. As you know from the previous examples, the call to sleep times the animation frame speed, and the call to repaint instructs the browser to make a call to update. But this is not an infinite loop. This loop only runs as long as running is true. If running gets set to false, this loop quits, causing the run method to return, and in the thread, when the run method returns, the thread dies. This kills the animation until the next call is made to start. That's about it for the unique part. The rest of the no-flicker applet is just like the application we looked at earlier. The value of x is updated to the new position of the circle. If the image file has not been initialized, it's done so now. The paint method is called to output the window into the memory resident image, and the draw image method is called to write it to the window. The paint method itself just simply fills the background of the window with green and draws the circle at the current location. The diameter of the ball fills the height of the window, whatever that happens to be, and the horizontal position of the ball is determined by the moving variable x. Compiling and running the applet looks like this. This lesson uses an animated applet to create a bouncing ball. The ball begins suspended in space and is pulled by gravity to the surface, where it bounces back up into space. Gravity then pulls it down again, and, well, you know how it goes. Things start getting repetitive. The Bounce 1 applet is the first attempt to get a bouncing ball. We have some calculations to do, and we want nice smooth motion, so the x and y positions of the ball are kept as real numbers. They'll be converted to integers as a count of pixels when they're used to actually position things in the window. But working with them as doubles keeps the calculations more accurate. The diameter of the bouncing ball is 10 pixels. The thing that causes a ball to get faster as it's moving down and to get slower as it's moving up is gravity, and gravity is a constant. So we make up a constant and declare it here. Why this particular value, you may well ask? Well, I tried several values, and this one looked about right to me. I suggest that you experiment with this applet and try some other values in here. You'll find that all the values work, but the larger the gravity, the harder the fall. I just like the speed that this particular number produced. There is something new here. Notice that the values diameter and gravity are declared as final. That means they cannot be changed. Whenever you declare something as final, you must provide an initial value for it, and it becomes a constant that can't be changed by the program. Both diameter and gravity are named constants in this class. At any given moment in time, the ball has a specific velocity. The velocity value is positive if the ball is moving down and negative if it's moving up. That way, all we have to do is add the value of the velocity to the current vertical position of the ball to move the ball to its next position. It's quite simple, really. Now, the ball isn't going to be moving horizontally, so the value of x is set and it's left alone. Setting y to 0 starts the ball at the top of the window, and setting the velocity to 0 means it's not currently moving. As the animation starts running, gravity will increase the velocity downward and the ball will move. In the update method, we test for the velocity being greater than 0. If that's true, it means the ball is moving down, so we test to see whether it's reached the bottom of the window. If it has, we bounce the ball. The velocity is switched to a negative number, and the position of the ball is adjusted slightly so it sits right exactly at the bottom. The velocity is then adjusted by the gravity. Gravity is always positive, so it always pulls down. If the velocity is negative, this action reduces its size, which slows the ball as it's going up. If the velocity is positive, gravity increases the velocity, bringing the ball down faster. The position of the ball is then adjusted by the magnitude of the velocity. The paint method does the same job it always does with a ball. It fills the background with solid color and then draws the ball at the current location. Notice the casting of the arguments to the call of fill oval. The method requires integer values for x and y, and we're using doubles, so that makes it necessary to cast them to the right type so the method will accept them. Here's how this applet runs. Notice how the ball gets faster and faster as it moves down, and it gets slower as it moves back up. Now, I know the motion is a little jerky here, but if you run this applet yourself, you'll see that it's actually quite smooth. But there's something that isn't quite right. It's always going back to the same starting place. It bounces all the way back up every time. That's not natural. Let's fix that. This is another version of the same program, but we've added friction. This statement right here introduces the inefficiency we need for reality. Each time the ball hits the bottom, it loses 5% of its velocity. This means it doesn't bounce as high as it did the time before. Let me show you. Now, let me suggest that you experiment with this applet a bit. Change some of the values and see what happens. This applet contains a number of the most fundamental things you'll need for animation. We've got a couple of more animated applets coming up, and you'll need to understand this one before you can understand them. This lesson explains about the generation of random numbers in Java. Random numbers come in handy for graphics, games, and for some statistical analysis. We're going to need some random numbers for purposes of animation in the next two lessons, so this lesson explores the process of getting them. This class lists a collection of 10 random numbers. The math class, which is in the Java Lang package, so no import statement is required for it, contains a static method named random that you can call to get a random number. Actual random numbers are a bit of a problem to produce on a computer for reasons I don't want to go into here, but the math random method does a pretty good job. It's certainly good enough for what we'll be doing. This program runs and produces 10 random numbers like this. And each time you run it, you'll get a different set of numbers. But this particular range of numbers is seldom what you want. All the random numbers are double values in the range of 0 to 1. If you want random numbers in the range 0 to 100, you'll need to multiply the value returned from the random method like this. Let me show you how this works. But for the upcoming applets, we're going to need to be able to produce random numbers in a range of integers. For example, we'll need to pick a random number from 5 to 12, or from -5 to +5. To make this easy to handle, I've written a method called randint. Now this program displays the output from calling the randint method 10 times with a range value set from a low of -5 to a high of 10. Now the randint method has a limitation in that it requires the low number be specified first, but this meant I didn't have to put in code to swap them if they were the other way around. The method's called a lot in the programs where I use it, and it just seemed cheaper and easier this way. Anyway, it works like this. This calculates the total number of possible values in the range between the lowest and the highest. The number in the range, then, is multiplied by the random number value, which is in the range of 0 to 1. Finally, the value of the low number is added to the result. This addition pulls the number into the requested range. It's a simple method, but it comes in very useful. Let me show you how it works. There you have 10 integer values in the requested range. And if you run it again, you get a completely different set of numbers. I've found that I develop lots of little goodies like this and use them over and over again. I suggest that you create a directory and collect little things like this because you wrote them and you know exactly how they work. Having a collection of such things can save enormous amounts of time down the road. This lesson describes the structure of an applet with a number of bouncing balls. Each one has its own trajectory and its own velocity. This is done by storing things in arrays. We begin by declaring the constant value count. It's sort of a tradition to put constants in all uppercase. It doesn't matter, but it does make them easier to spot. This is actually a tradition adopted from defined constants in C. Anyway, we're going to have 10 bouncing balls, so we need to keep track of the position of each one of them independently. That's what the X and Y arrays are for. The arrays are doubles, just as they were in the previous bouncing ball applet, and the size of the array is determined by the constant value count. Each ball will have its own velocity, so we need arrays to keep track of those also. In this program, not only does the ball have a y velocity for its vertical movement, but it also has an x velocity because we're going to move them horizontally as well. Each one is going to bounce across the window and disappear off to either the left or right, at which point it will be dropped back in from the top to do it all over again. Each ball has the same diameter, and the value of gravity is the same for all of them, so there's no need to have arrays for these values. In the init method, we grab a rectangle object so we'll know the size of the playing field, and the value of x for each ball is initialized. The value of -100 was chosen, so the balls would appear to the update method to be fully off stage left. That way they'll be restarted. Let me show you what I mean. We now have more than one ball, so the update method is going to have to address each one of them individually. This is done in a for loop that executes once for each member of the array. This if statement checks to see whether the ball is currently between the two sides of the window. The question here is this particular ball less than minus diameter, which means it would be off stage to the left, or is this particular ball greater than the rectangle width, which means it would be off stage to the right. That's why the initial x position of each ball was set to -100 to guarantee that this would be outside the window. The x and y positions of the ball are set to their starting point. Randint is used to position the ball horizontally at some point between the two sides of the window, and it's used again to place the ball vertically in space at some point above the window. The velocity, the vertical velocity of this ball is set to 0, so it will start to fall from its random position above the window, just as if pushed down by gravity. Now, we want the ball to have a slight sideways motion, so it won't just bounce up and down and stay in the window. This is done with a third kind of loop, the one I haven't shown you yet. This is sort of an upside-down while loop. Notice that the conditional test is at the bottom. That means the body of the loop is guaranteed to execute at least once. That is, when the execution comes to the do statement, the body of the loop is immediately executed, and then, at the bottom, the test is made to see whether we do it again. This continues until the condition is false and the looping quits. In this case, we want the x velocity to be some value between -2 and 2, but not be 0. We just keep getting random numbers in the range until we get one that isn't 0. Just as we did in the previous applet, we check to see if the ball is moving down. If it is, we check to see whether it's reached the bottom. If it has, we bounce the ball by reversing its direction. The vertical velocity of this ball is adjusted by the pull of gravity. Notice that we never modify the x velocity. The horizontal speed is assigned when the ball is first dropped, and it never changes. The position of the ball is then adjusted by its two velocity components, and we're at the bottom of the loop, ready to start over and do the same calculation for the next ball. The paint method contains a loop that paints each ball in the array at its current x and y positions. I put the randint method here at the bottom for no particular reason. It could have been placed anywhere in the applet. It's just a habit I have of placing utility methods at the bottom of a class. It doesn't make any difference. It's like the compiler looks at the whole thing at once to see what's there before it starts compiling. The order of methods makes no difference in any way. Anyway, this applet bounces balls. Now, let me say again that because this has been recorded and is being played back, the motion is just not very smooth. But you should be able to get the idea. You should really run this applet for yourself. Here, let me show you something. Making this one change will change the size of all the arrays and the number of times it executes all the loops. This version will bounce 100 balls. This lesson pulls together several elements from the previous lessons to create an applet that displays leaves falling down to the bottom of the window and blowing away. Over the top of this picture, the current date and time is constantly updated. It may not be the most advanced applet in the world, but it can tell time. These constant values are defined to indicate the window will have 100 leaves falling down and that there are 4 images for the leaves. The picture of each leaf is in a GIF file and there are 4 of them. Each of the falling leaves will select one of the images. This is the string reference that will be used to hold the date string to be displayed, and these are the XY locations for it in the window. Notice that the string object is initialized to a blank string. There's a very good reason for doing that. I'll tell you about it when I get to the paint method. This is the array of image objects that's going to hold the leaf images for us, and these are the X and Y positions of each leaf as it falls. You may have noticed that we're not using double values for the locations this time. That's because it isn't necessary to have smooth motion. As each leaf comes down and blows away, we actually jiggle it a little. Here we select a nice font for displaying the time and date. And right here we set a bottom value. This value is compared against the Y position of a falling leaf, so we can determine when it reaches the bottom of the window. The leaf images are 20 pixels tall, so if a leaf is inside 18 pixels from the bottom of the window, we quit making it fall. We load the leaf images from the server and store them in this array. We add each one to the media tracker, and we wait for all of them to load. Finally, each leaf is positioned horizontally off to the right, so the update method will assume it has blown away and will drop it from the sky again. This for loop in the update method moves each leaf in the array to its next position. A leaf can be treated in one of 3 ways. If the leaf has been completely blown out of the window and is off stage right, we set both its X and Y values so it'll drop from the sky again. Vertically, it's placed out of sight at a random distance above the window. Horizontally, it's placed randomly between the 2 sides. Actually, it may be placed a bit to the left of the window because the leaves blow over to the right, and if none ever went all the way over to the left, the lower left end of the window wouldn't have a leaf. You'll see what I mean when you see the applet run. Now this else-if combination in the syntax can be used if you have more than 2 options to choose from. This isn't any kind of special structure or anything. It's just a consequence of the natural syntax of Java. I kind of like this else-if form, so I tend to use it a lot. Here, if the leaf has fallen to the bottom of the window, the horizontal position is adjusted somewhere between 0 and 2 pixels to the right. Using a different value each time adds to the jerky movements, and that adds to the charm of the applet. The vertical position is moved up or down 1 pixel, or it is left where it is. This is also for the purpose of adding jiggle. If neither of the 2 previous cases were true, then this must be one of our falling leaves. The horizontal position is changed to the right by as much as 2 pixels, or it may be left where it is. The vertical position is increased by 1 pixel, causing the leaves to all fall at an even speed, but they wiggle a bit while they do it. This is an example of using a Java class without naming it on an import statement. By using its full name every time it's referred to, we don't leave anything undefined for the compiler to search for. Anyway, we create a date object without an argument, so it contains the current date and time. The date class of Java has lots of methods for doing arithmetic and comparison of dates and times. It keeps time to the nearest millisecond and has a range of several thousand years in both directions from where we are right now. We don't have to worry about another Y2K problem for quite a while, probably until the year 10,000, when they find that COBOL needs another digit. Just like any other object, the date object can be converted to a string by calling the toString method. This string is the one that we want to display. Using a font metrics object, we calculate the X and Y positions required to center the string in the window. In the paint method, this loop paints each of the images in its current XY position. This line of code is used to select the image to be used for each leaf. There are a lot more leaves than there are images, so the index into the array of X and Y leaf location is divided by the number of images, and the remainder is used as the index into the array of images. This is the modulo operator that we talked about earlier, and it seems to come in handy in the darndest places. Here the color and the font are set for the string, and the string is drawn on top of everything else in the window. It could have been drawn earlier and the leaves would fall in front of it, or you could even draw some of the leaves before it and some after it, and some of the leaves would go behind and some in front. Anyway, I mentioned at the beginning that it was necessary to initialize the banner string. The reason for that is the web browser may call the paint method before you're ready for it. If, when you spawn a thread to do the animation, the web browser decides to make a direct call to paint first, a null string here would give you a problem. This happens a lot with threads being asynchronous. Just remember this: the paint method should always be ready because it can be called at any time after init, even before start. Never trust a web browser. Program defensively. When you run this applet on your system, you'll notice that the time is the local time for your computer. I can see by the time here I've missed lunch, so I've got to go.